Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, continuous subarrays. The problem is very interesting and it can be solved in various different ways, in various different time complexities as well. For example, you can use binary search and segment trees to solve this in order n log square in solution. You can use two pointers and usual sets to get a order n log n solution. Or you can use simple stack and the good old next greater or previous greater element, and you can solve this in order n time as well. We will be discussing each of these solutions in this video, so stay tuned till the very end, and I'm very sure you will be able to understand some new concepts after the end of the video. If you are interested in just specific section or a specific solution, I have attached all the timestamps in the description below. Feel free to check it out. With that, let's get started. The problem states that we are given a zero indexed array nums. A subarray is called continuous if for every pair of indices i1, i2 in this subarray, this condition should be satisfied, right? And we have to return the total number of continuous subarrays. Let's take an example. Let's say this is the given array. Let's start with subarray of size 1. So if you take subarray of size 1, there are 4 possible subarray of size 1. And each of these subarray is a continuous subarray. Why? Because there is only one. If you talk about these pairs, there is only one possible pair possible, which is this particular index itself. So if you take numsci1 and numsci2, numsci1 and numsci2 are equal, so the value of numsci1 minus numsci2 modulus would be 0 always, and hence this condition is always satisfied. Therefore each subarray of size 1 is a continuous subarray. Similarly, there are 3 possible subarray of size 2, and these 3 subarrays are also continuous subarrays. How? If you think about it, for each of these subarray, there is one possible pair which is not which is different, where i1 and i2 are different, and for each of these pair the difference is already less than equals to 2. So here the difference is 1, here the difference is 2, and here difference is 2. So because difference is less than equals to 2, these 3 subarrays are also continuous subarray. Finally, for the size of 3, 5, 4, 2 is not a continuous subarray. Why? Because if you take i1 as 5, i2 as 2, the difference between them would be 3, which is not less than equals to 2. And because the condition needs to be satisfied for each pair, 5, 4, 2 is not a continuous subarray, because there is at least one pair for which the condition is not satisfied. And finally, for 4 to 4, the 4 to 4 subarray is continuous subarray, because for each pair the condition is already satisfied. So in total we figure out that there are 8 subarray which we found that satisfies this condition, and hence 8 is the answer. Now how to solve this? So we'll start with the first solution, wherein we'll use 2 pointers. We'll see actually how to approach or how to come up with 2 pointers solution in the first place. So whenever a modulus is involved, right, the problem becomes a bit tricky, because you don't know which of these is greater or which of these is smaller, right? So whenever modulus is involved, just try to remove the modulus as the first step always. So in this particular scenario, we can actually remove this modulus completely. How? If you haven't thought about it yet, I would encourage you to pause and think for a moment. Think about this condition. For each pair, this condition should be satisfied. Now, if for the maximum value of this pair, if the maximum value of this numsci1 minus numsci2 satisfies this condition, you don't need to check for any other condition at all, right? Now what can be the maximum value of this expression? The maximum value would simply be max minus min, right? You will say, okay, I know the maximum in the range i1 and i2, I know the minimum in the range i1 and i2, I will simply subtract them, and that will give me the maximum value of this particular expression, right? And because you are dealing with maximum and minimum, you can simply avoid the modulus completely, because you know max should be greater than equals to min. So this condition, you can remove this condition or replace this condition with simply this particular condition. You can say, okay, if max minus min is less than equals to 2, then I am certain that for each pair this condition will be satisfied, right? So we can get rid of this condition, and the new condition for us is now this, right? Now this, like, how will you code this in brute force manner? Like, very simple, right? You can just simply do a check each subarray, get the max and minimum of each subarray, and see if it is less than equals to 2. If it is less than equals to 2, add it to our result. Otherwise, just skip it, right? So the pseudo code for that would look something like this. We can iterate over all subarray L to R. So we'll start with L as 0, right? And we will iterate over all possible R. So we can say this is the first R, this is second R, this is third R, and so on and so forth, right? And for each subarray, we will get the maximum and minimum, and if that satisfies this particular criteria, that will be a good subarray or a continuous subarray, and that we will increment our result. Now think about it. If L to R is not a good subarray, L to R plus 1 will never be a good subarray, right? Because if you add one element, that element can increase the max or can decrease the min. It will never decrease the max or increase the min, right? And because of this, if L to R is not a good subarray, L to R plus 1 will never be a good subarray. So we can, that's why we have put a break here. We can simply say that if the first R where we find this condition to not satisfied, we will just simply break out from there, right? Now this solution is of order n square complexity, which will not pass because the value of n in the problem is 10 to the power 5. So n square will not pass. We have to optimize this. So optimization simply means that we have to get rid of this particular for loop. Either we have to reduce the number of iterations in the for loop, or we can do some binary search or something to get rid of iterating over all possible r's, right? Now in this type of problem, just think about if you can actually skip iterating over all possible r starting from L. So in this particular scenario, what we are doing is we are saying that whenever, let's say previously L was this and R comes at here and it breaks out, right? Now whenever you increment L, you reset the R to this. So that's where you have to iterate over, or you can iterate over order and elements again. But if you can somehow prove that if L to R is valid, L plus 1 to R is also valid, in that case you cannot, you will not required to reset R to L. Instead you can start R from where it was left, right? And that will make sure that you are only iterating over order n elements over the entire lifetime of this nested loops. So the complexity would then become order n, right? That is simply two-pointer approach. Now in this particular problem, it is possible. How? Again, the exact same argument is applied which we applied for putting this break part. So we know that L to R is valid. So it means L plus 1 to R will always be valid. Why? Because number of pairs, like for each pair we need to satisfy this condition, right? So number of pairs in this subarray will be a superset of number of pair in this subarray, right? Because, and if the condition is satisfied for the previous subarray, then for the new subarray condition will always be satisfied, right? So what we just proved that we don't need to reset R. Wherever R was there, R can still stay there, and we can simply keep on incrementing R as per our need. So this solution will now change to something like this. So we can simply say that, okay, for each L, we will keep on iterating over the R until we find a bad R, or until we find a point where this R is not satisfied with this particular L. Whenever we find that particular point, we will simply add result as r minus l, and then because l is now done, like we are incrementing l, so the index l is now done, we will simply remove l, right? Straightforward two pointer approach. So the main thing you have to understand here is how we are able to apply two pointers, or why we are able to apply two pointers, and I think you got the reason as well. Now, what will be the time complexity? Time complexity will simply be order n here. Why? Because we are simply iterating over, like r, the value of how many possible values of r can be there. So it can be order n, because r is simply getting incremented every time. And in the same fashion, L is also simply getting incrementing every time. So in total, the amortized complexity of this entire nested loop will still be order n. Now, our problem doesn't end here. Why? Because to figure out whether the current subarray is good or not, what we need min and max, right? And we are also adding a new elements. We are also removing a new elements. So previously we were not removing any element, so min and max were simple to calculate. But because we are now removing the elements as well, min and max will not be straightforward to compute. So what we need a data structure that can actually give us the max of all the elements, the min of all the elements. It can support addition of an element, and it can also support removal of an element. So what is the data structure that can give us these functionalities? Again, encourage you to pause and think. The data structure that can give us all of these is balanced binary search tree, and in most of the languages there is a built-in implementation of set, which can give you all these functionality in just order log n time. And all these functionalities, you have to put a multi-set here. Why? Because there can be duplicates in the given array as well. So with just multi-set, what you have done is this addition will now not an order 1 operation, but rather it will be an order log n operation. And similarly, to check whether the given subarray is good or not, this is also not a order 1 operation now, this is also an order log n operation. And in the very similar fashion, remove is also order log n operation. So in total, the entire complexity now is order n log n, right? And this will surely pass the given time constraint. Now, if you have watched till this point, I would encourage you to pause and try to code this solution yourself and get it accepted as well. Next, we're looking at the code before jumping into the next possible solution. So the code is very straightforward. As we have discussed, we have taken a multi-set that will be able to give us all this functionality in order log n time. Now we are just iterating over L from 0 to n. We iterate over R until we figure out a bad R. So basically, we will keep on adding R, and the first R after which this condition is not satisfied, we will break out from this while loop, and we'll add this R minus L to the result. Notice that we are not adding R minus L plus 1. Why? Because the rth element is not a good element, because after adding the rth element, this condition was unsatisfied. So rth element was not a good element, and hence we have to skip R itself. That's why we are just adding R minus L. And finally, we'll erase the nums L as well from the given multiset. So the entire complexity as we discussed is just order n log n, and the space complexity is order n. So next, let's look at how will you solve this if you are not able to make this observation, right? So basically, this solution involves that you make two observations. First, that you can break out from the loop, and second, that you can actually remove this for loop with just a two-pointer approach. So this part is tedious or tricky in some scenarios. So here it was straightforward, but it can be tricky in many scenarios, and you might not be able to observe or make this observation in a live context setting itself. So if you are not able to make this observation, what you can simply do, you can simply do this exact same, apply the exact same algorithm with a different approach. So what we will say that, okay, this was the initial for loop, right? Initial solution, order n square solution. Now we have to reduce this. Basically, you have to remove this particular for loop. So we are here searching for R in a linear fashion, right? What we can say that, okay, instead of linear search, can we apply binary search? If yes, this R, like this for loop, can simply be removed with the binary search, and we'll get the maximum R, or the last index R, up till which everything is satisfied. So for each L, you can get the R in just order log n time, and hence the entire complexity would just become order n log n, right? Now, how to apply binary search, or if you don't know about that, there's a complete video. I would link that somewhere in the description down below or top right section. You can watch that out. In essence, what it says is, you will, like, you have some sample space. You divide the sample into half. Now, if you are able to deterministically say that I will only search in the left half and skip the right half, or I will only search in the right half and skip the left half, then binary search is applicable here, right? So in this particular scenario, let's say for a particular index I, or for a particular R, the condition is satisfied. Basically, we know that for some index L, this particular R is a valid R. Now, if this R is a valid R, do you need to check R minus 1 or R minus 2 or R minus 3? The answer is no, because if R is valid, you already know that all of these are valid, right? So what you can simply say that, okay, if R is valid, I will simply search in the right half and I can completely skip the left half, right? Similarly, let's say you figured out that, okay, R is not valid. So basically this L and this R, you figure out what is the min in this range, what is the max in this range. The difference between them is greater than 2. So basically this is not valid. So if this is not valid, is there any sense to search in the right half? The answer is no, because the max in this range itself is greater. Like max minus min in this range itself is greater. So if you increment R, it will never be smaller, right? So that's where we can simply skip the left half and only search in the right half. So notice that we are, for a particular index, for the answer of a particular index, we are able to deterministically say whether to search in the left or the right half, and hence binary search is applicable here. Now, what you can simply do, you can simply replace this particular inner loop with a binary search, and this will be your answer. So this line can also go away. So basically this will be the new algorithm, which will run in order n log n time. Now let's look at what binary search here is, like how binary search is implemented here. So binary search would be something like this, right? You will say, okay, I need to search for R. Okay, so this is a bit different. So let's say there is a starting point as well, S, right? And this would be S and S, right? Basically binary search here is a bit different than usual binary search, because you need to start the search from L, and L is different for each binary search that we are doing here, right? So that's where we take in three things here. The range in which we need to do binary search, and the starting index, which is the starting index of the current subarray, right? So if like this is the usual binary search, while L less than R, you will simply go to the middle part, and now you will see what is the max in the range S to m plus 1, what is the min in the range S to m plus 1. If the difference is less than or equals to 2, you know that you can search in the right half. You can completely skip the left half. Otherwise, you have to search in the left half as well. You have to search in the left half and you can skip the right half. So basically, here, if you look at it, the complexity is order log n, given that you are able to figure out max and min in order one time. But you can't do that, right? If you do naively, that will require order n time to figure out max and min. And that's where exactly segment tree will help. Segment tree can give you max and min in order log n time as well. So basically for each iteration, you are calling segment tree to get the max and get the mean. So this will require 2 log n time to get the max and min, and you are calling that log n number of times, right? Because in binary search you will have log n number of iterations. So for each iteration, again you are calling segment tree that will take order log n time. So the total complexity of this binary search itself is log square n, and you are calling this binary search n number of times. So overall complexity of this entire algorithm is order n log square n, right? Now this, if you don't know about binary search or if you don't know about segment tree, there is a complete series of segment trees that we have started, in which we are trying to dissect segment trees from scratch. We already have solved the basics and some intermediate level problems there as well. If you haven't watched that yet, I would link the playlist in the description below or somewhere in the top right section. Make sure to check that out and follow along if you like it. So I am not showing you the code for this particular approach because this particular approach is very straightforward. You just need to write segment tree to get max and min, and everything else is a very straightforward thing. So, but I would strongly encourage you to code this entire solution by yourself, because that will give you much better understanding, and that can be one more problem that where you can apply segment tree and practice. So next we'll be looking at the final solution, which is utilizing the next greater and the previous greater element and solving this exact same problem in just order n time. How? Let's look at it. So first of all, how can you get to this point, or how can you think in the first place that this kind of solution can work? The main thing where you can get this idea is, notice that you need to see the value of num psi 1 and num psi 2 should be less than equals to less than equal to 2, right? So we already have saw that the given constraint can be simplified into this particular constraint. So what you can say that, okay, I need to optimize this loop. So if you haven't thought about these two solutions, it means you somehow missed that you can apply binary search here. So this part is gone. You somehow missed that this entire for loop can be removed by using a two-pointer approach, and by proving that the correctness of that particular approach. So in that case, you are left with this particular two nested loop, and you are stuck there. So that's where what you should do is you should try to think of another way of this particular nested loop. So what you can say that, okay, anything is not working here. So what I will do is I want max minus min to be less than equals to 7. So what I can do, I can just simply fix the max. I will say, let's say this is the max always. Now I will figure out how many subarrays are there for which this number is the max, and the difference between this number and the min is actually less than equals to 2, right? Again, just to reiterate, we'll just figure out the subarray for which this number is the max and the difference between this and the min is less than equals to 2. Now, as soon as you saw that, okay, a particular number should be max, immediately it should be clicked that we can use next greater and previous greater element, right? Because we want this number to be max, so we can simply figure out what is the next greater element and what is the previous greater element, and whatever that comes out, that range is the range for in which this particular number can be valid, right? Or the subarray can be valid. Now let's say you figured out that, okay, this range is the valid range, right? Because the previous greater element is 8 and the next greater element is 4. So because of this, you figure out that, okay, 6 is maximum in this particular range. Now you need to also check whether in which range 6 is minimum as well, right? Or basically 6 minus minimum is less than equals to 2 as well. You have to check this as well, right? So for that, you can utilize the previous smaller element and the next smaller element. So what you can say that, okay, I will figure out what is the next smaller element. So next smaller element of 6 is 4. Now if difference between 6 and the next smaller element is less than equals to 2, I will move further and figure out what is the next smaller element of the next smaller element that we got. And we will keep on doing this until we reach a point where the difference is less than equals, where difference become greater than 2. And how many times you have to apply this operation? Maximum 2 times, right? So from 6 you will reach 5, and from 5 you will reach 4, and from 4 you will reach 3. So basically you have to apply, 3 times. Basically you have to apply this operation a maximum number of 3 times, and in 3 times you are sure that the condition will be violated, because the in every iteration you are decrementing 6, or you are going to an element which is at least 1 less than the previous element, right? So with this we are always sure that in 3 iterations we will be reaching to a point where the condition is not satisfied. So what you can do, the algorithm is very simple now. For each element you will say that, okay, what is the answer if this is the maximum element? So you will figure out what is the next, or what is the maximum value of R possible for this particular index. You will figure out what is the maximum value of L possible for this particular index. How will you figure out L and R? You will figure out L and R by simply iterating over the next smaller elements until you hit a condition where this particular thing is unsatisfied. So in the similar fashion you will go back and figure out L. Now once you have L and R, notice that this L and R will not let's take this example itself. Let's say you are figuring out L and R. So for this particular index I, what will be the value of R? The value of R would be this, right? Why? Because you will go from 6 to 4 first, and then you will say, okay, 6 minus 4 is less than equals to 2, so you will move forward. So from 4 you will go to 1, and now as soon as you go 1 you will see, okay, this is not satisfied, so this is the value of R that is possible. Now what is the value of L? You will go, what is the previous smaller element? You will reach at 5, so you can say, okay, 5 is good. Now what is 6 minus 5 is less than equals to 1, so this is good. Now I will go to the previous smaller element of 5, so there is no previous smaller element at all, so you will say, okay, this is the value of L, right? Now in other words, what we are saying is this number or the subarray in this range will have, if this number is maximum, then all the subarray in this range will be a continuous subarray, or will be a good subarray, right? But look at it here, we have 8 as well. So the condition was this subarray will be good, every subarray will be good if 6 is the largest element, right? But here we saw that if 6 is not the largest element, then the condition might not be satisfied. So this L and R are tentative L and R, right? Actual L and R we will get if you can say that, okay, 6 is the largest element in this range. So for that you can simply use next greater element and previous greater element. So previous greater element of 6 is 8. It means 6 is largest in this range itself. So what you can then say is, I will update L to this particular index, and in the same fashion you will figure out where 6 is largest in the right side. So you will figure out, okay, 6 is largest in the right side in this particular range, so you will again update R to that particular index. Now once you have got L and R, the calculating the number of subarrays that is good, which contains 6 as the maximum number, is very simple. You can simply let's say this is I, you can say L minus I plus 1 multiplied by R minus I plus 1. That will be the answer. Now why that will be the answer? Basically, let's say this is for some hypothetical scenario, let's say this is L and this is valid R. So what you can say that, okay, I want 6 to be included because 6 should be there to make 6 as maximum. So I want 6 to be included. So how many subarrays will be possible? This is first subarray, which includes L to R. This is second subarray. This is third subarray. And then you can say, okay, I will update L to okay, sorry. You will say, oh, I will update L to this. So now again this is one subarray, this second subarray, this is third subarray. Now we will again update L to this. You will say okay, this is first subarray, this is second subarray, this is third subarray. Basically, for every L in the range L to I, you will be getting I minus R plus 1 number of subarrays, right? And hence the you can say I minus L multiplied by R minus I is the total number of good subarrays that you can get, given 6 is the maximum. So the pseudocode for this would be very straightforward. We will just figure out all these things: next smaller, previous smaller, next getter, previous getter. All these things can be figured out using stack simply, and this entire thing can be done in just order and time. Right now, after you have done this, what you can do, as you discussed, for every I, you will assume that this I is the maximum number, right? So this I is the maximum. So you have to figure out what is the previous minimum, what is the value of L and R, right? So for L, as we have discussed, we will keep on going backwards as per the previous smaller element until we hit a condition where the number we are landing is not satisfying the given constraint. Now this while loop, we are very sure that this will be run at most 3 number of times. So this while loop is nothing but a single 3 iterations, which makes it just order 1 operation. So after you get a particular L, you also need to make sure that I is the maximum in this range. So that's where you just make sure that L is maximum of L and previous greater of I. In the very same fashion, you will figure out R by using the next smaller and next greater. So it will be greater, right? Sorry for that. Now once you get L and R, you can simply add this particular thing in the result, right? Now there is one small edge case in this entire solution. The edge case is there can be duplicates as well, right? So you can there can be the scenario where 6 repeats again. So if that's the case, you have to make sure that 646 is counted exactly once. Why? Because you may have the tendency to count 646 when this particular 6 is maximum, right? And you may also count 646 when this particular 6 is maximum, and hence we will have double counting. So the very smart or the very simple solution for that particular problem would be, when you are finding out the next greater and previous greater, for one of them you will use the condition greater than equals to, and for other one you will use greater than. So that will make sure that you are only counting 646 once. Basically you are saying that for this 6, the this anything in the left is greater than this 6 itself. So basically any 6 in the left is greater than this particular 6. But for this 6, you are saying that anything in the right which is equals to 6 is greater, right? So that's the main edge case that you need to tackle if you are solving by this approach. Let's look at the code. The code is straightforward as again. What we are doing, we are simply figuring out next smaller, previous smaller, next greater, previous greater by using stack. Let's look at one of them. Very simple. We are simply removing all the elements which are greater than the current one, because for anything after this, j will contribute to the answer. So that's where we just simply remove the previous ones and updated our previous smaller index. In the same fashion, you will figure out previous greater, next smaller, and next greater, right? And after we have done all of them, we will simply iterate from over I from 0 to n. Figure out L and R. How we will figure out L? We have discussed previously. And once you have L and R, you will simply figure out, or you can simply do R minus I plus 1 and I minus L plus 1. Multiply them, and that will be the number of subarrays that is good, for which I is the maximum, right? And if you do this for every I, we'll get total number of good subarrays, right? Now if you have watched till this point, there is a small follow-up or a small exercise that you can try. Try to solve the same problem using all the 3 methods when this 2 is not 2, like it can be any x, right? So you can see this, if the 2 is not 2, it is x, you can easily apply this algorithm without any issues. You can also apply this algorithm without an issue, but this algorithm you will not be able to apply, because this while loop will then expand, because this while loop was currently just order 3 operation, because the value is 2 here. If it increases, this will be equals to that value x, right? Now this x can be reduced to log x as well, and that is your exercise. You can use a hint is binary lifting. You can use binary lifting to make this x log x. I have explained binary lifting in terms of LCA. I will try to link that video in the description down below. But make sure that you at least give it a try. It is very interesting. And if you are able to do it, just paste solution in the comment section below so that others can refer to it. So that's it in this video. If you have any doubts in any of the 3 approaches, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.